So multiplication. You see, we start off the same way, still draw the two individual ones, but now we're interested in some other things because we're multiplying rather than adding. Whether it's positive or negative, and we're just using the basic idea of positive times a positive gives a positive, positive times a negative gives a negative. And that can give us the region in the number plane, whether above the axis or below the axis for different sections. So that means important points, obviously, is where either function is equal to 0, because if you multiply by 0, you're going to get 0. So that'll stay as an x-intercept. 1 becomes an interesting point, wherever y equals 1, because multiplied by 1, then it's going to stay the same, because 1 times anything is itself. So one way of approaching this, similar thing, discontinuities. So once again, even when we multiply them together, that discontinuity is still going to exist. I suppose the classic one for this one is if you were to draw the line y equals x on x as opposed to drawing the line y equals 1. See, y equals x on x, yes, it's a horizontal line, and it looks like y equals 1, but it would have a discontinuity at x equals 0, because you couldn't substitute into x on x for x equals 0. So it's a subtle difference between the two. So as I was saying, x-intercepts, function x equals 0, gx equals 0, then obviously when we multiply them together, they're going to become 0. Symmetric graphs will retain some form of symmetry. Now, what do we mean? It's not necessarily going to be the same symmetry now, because odd times odd will actually give us an even function. I suppose the simplest one to explain there is y equals x is an odd function. So if you went y equals x times y equals x, you get y equals x squared, which is our parabola, and that's an even function. So odd times odd will give even. Even times even also is even, but odd times even will be odd. So let's have a go at this one. I've already factorised it to make life a little bit easier. Y equals x squared, x plus 1, x minus 1 cubed. So the three basic curves there are drawn in blue, red and purple. Okay. Now, they're not asymptotes I'm drawing in there, because obviously there's no asymptotes with this one. That's what I'm saying. I'm breaking this up into boundaries where it's going to change from positive to negative. Because basically, there's our x-intercepts, and what we were saying were the x-intercepts will stay as x-intercepts. So each one where I put those green dotted lines, where it hits the x-axis will be x-intercepts. But I now know that on the left-hand side of that first dotted line, I'm going to get a positive, so red's positive, times a negative, blue's negative, times a negative, purple's negative. So I know the answer will be a positive number. So I know the curve will be above the x-axis for that section. So in between the next two, I do the same sort of idea. I've got positive times negative. Well, that one's going to be negative. Next one, positive times negative again. So that's also going to be below. Now straight away, that tells me a bit of information. Because if I know there's an x-intercept at the origin, but it's staying negative, that must be a turning point. Let's turn there, go up and come back down. That just leaves us with the last section, positive times positive, which is positive. So I now know the regions where this graph is travelling. There's our x-intercepts, let's dot them in. Remember, we know some things from polynomials as well. We know those x-intercepts will act like the individual root. So this cubic, x minus 1 cubed, when it comes through this x-intercept, it will come through it like a cubic. It won't be a straight line. And, a bit hard to see that. Did I get rid of the... There we go. So the light green one there, unfortunately my scale looks like that's a dead straight line, because I actually did this on a computer package to draw it, and the scale was a bit low. That actually does come down and turn and come back up in there, even though it does deceptively look like a straight line with my scale. Now, division is the same as multiplication, because all you're really doing is multiplying by the reciprocal. So you've still got exactly the same ideas. The difference being, though, when this function on the bottom is equal to 0, you're not going to have an x-intercept. You'll end up having an asymptote, because it's undefined there. So again, we would draw them separately, So for this example, let's do x plus 1 times x minus 2 over x plus 2, x minus 1, which is 4 straight lines. The vertical asymptotes, well, that's where the bottom of the fraction is going to equal 0. So that will be x plus 2 and x minus 1. So the red ones are actually asymptotes. But those asymptotes also create boundaries to check when you're talking about, is it above, is it below? Now I'm going to do the shading in the regions. So I'll do it a slightly different colour and a smaller dot, you'll notice, not to confuse them with my asymptotes. You don't really need to draw the lines, as long as you know there's boundaries there. And so we've got negative times negative times negative times negative, which is positive. Positive times negative times negative times negative is down there. Then we go back up. Then we're back down. Oh, isn't that lovely? Up and down, up and down, up and down. There's the regions we are in for that curve. X-intercepts then will be where I've put the two blue lines. Y-intercept. Remember, y-intercept is just when x equals 0. It's still very easy to find. So in this one, it turns out to be positive 1. Now, what about horizontal and oblique asymptotes? With these sort of functions, as we know, we often get them. Polynomial division, dominance. If it wasn't a polynomial one, you might look at things like, if it's e to the x times sine x, we know e to the x is going to dominate. So out at infinity, it'll go off to infinity, things like that. But this is a polynomial one, so we do our division, and I end up with y equals 1. So we've got a horizontal asymptote for this one. So y equals 1. So let's put that in. Now, clearly, this one does cut the asymptote, because we've already plotted that point in. So we know it's going to cross the asymptote there. We bend towards the asymptotes. We've got to pass through those x-intercepts. We've got to be in those regions. So this first region, I'm sort of, not much I can do. There's no x-intercepts. I've got to stay in the pink. I've got to bend towards the asymptotes. It must be like our classic hyperbola in that section there. Okay. Similar thing, is that going to happen? No, because remember, that's not an asymptote. That's actually just my boundary line. Over here, I've got a vertical asymptote. It'll go through 0. It'll come up. Now, we must keep going up then and bend towards that asymptote. A bit like a cubic or a tan curve, doing that sort of inflecting as it comes through. The last section, I've got to bend towards this asymptote, come through my x-intercept, and I'm going to stay under the asymptote in this case because there's no other points where I cut it. So there it is there in the blue colour. Get rid of the pinks to make it a little bit easier to see. A lot of mess there because of the computer package I've used, but those blue lines is where that curve would be. Okay, sine x on x. So we've got y equals sine x on x. There's y equals x. There's y equals sine x. I didn't bother marking in the x-intercepts for this one. What we're saying is we're getting that red sine curve. We're dividing by the blue line. So we're going to divide by bigger and bigger numbers. We know sine will stay in between -1 and 1. And we're going to divide by bigger and bigger numbers. So what's going to happen? It's going to get smaller and smaller and smaller. So it'll still wind along the x-axis, but it'll just keep getting smaller and smaller until eventually it looks like it's just the x-axis itself. But the other interesting one is what happens here, and that's when we have to remember our limits, and the limit is 1. So I know that it's going to meet here at 1. Not going to exist there, so it'll be a point discontinuity, and we'll have something like that. Let's get rid of those curves. So we've got a curve that is winding along the x-axis, but the peak getting smaller and smaller. Yeah. So we're not actually saying 0 on 0 is 1. If you were to sub in a really small number into that, you'd find it's very close to 1, the answer. So yeah. If you had x on sine x, then it would be getting bigger, because y equals x is getting bigger, but you're dividing them by numbers that are always in between 1 and minus 1, so a fraction if you like. So divided by a fraction, it's going to get bigger and bigger. I forget what the other options were. Might look that up in a sec, see what those options were. So, okay, 8C.